In this video, we're going to learn a few more things about acids and bases and their reactivity. So first things first, one thing you have to know is that any salt can be made from an acid and a base. And salt is a pretty broadly defined type of substance. Basically, any ionic compound that is not a hydroxide will be a salt. So for example, if we have NaCl, the thing that you know of as salt, that comes from the reaction of an acid. Well, an acid has to have an H plus, and then needs a negative part. Oh wait, that's the chloride here, HCl. And then the base is, well, it needs to have hydroxide if we're reacting it with H plus to give you water. So it's something with a hydroxide, and there's sodium here. Oh, it's just NaOH. So our acid is HCl, our base is NaOH, and they'll react together to give you a salt and water. Similarly, we can get CaCl2. CaCl2 is the stuff that you use most commonly as a de-icer in the wintertime. I mean, you might also use sodium chloride, but this is also very common. And this comes from calcium hydroxide and 2 hydrochloric acids. And to make this balance, we need to have 2 waters. But you can also have a salt like, let's go with aluminum nitrate, AlNO3 3 plus 3H2O it's going to be. This comes from, the aluminum has to be with hydroxide, and aluminum hydroxide has the formula AlOH3, and we need 3 nitric acids to make this happen. The nitrate comes from nitric acid. The aluminum comes from aluminum hydroxide. That's it. So another thing, when we look at Cr in parentheses OH2, that looks like a chromium hydroxide. And the way it's presented to us, it suggests, oh, this is a base. Then we also have H2CrO4, which is presented like an acid because the H's are out in front. But if not for the way that they were presented, you might wonder, how do you tell? Like if this were H2CrO2, if that's the way it were mentioned, or some other way, CrH2O2, whatever, and it didn't have the hydroxide in parentheses, how would you know if this is an acid or a base or neither? Well, this is going to be a base, and we can explain that just by looking at how partially positive the chromium is in each of these 2 compounds. So if I look at the Cr in this case, I know if I look at the oxidation numbers, my hydroxide needs to be -1 overall, and if I've got 2 of them, my chromium is +2. By contrast, over here, I've got 4 oxygens, each is -2, so that's -8 from the oxygens. I know if this is acting as an acid, we have 2 times +1 for each hydrogen, so that's 2. And so to get us back to neutral, we've got -8 and +2. We need to have the chromium be +6. So the chromium on the right is much, much more positive than the chromium on the left. That makes a big difference here. Because if I've got a chromium bonded to an oxygen, bonded to a hydrogen, and this chromium is only +2, then this chromium isn't going to be pulling the electrons towards it as much in this case. And so that oxygen is able to be a little bit more partially negative. Essentially, this bond between the Cr and the O is not very strong, and it can break, and we can get hydroxide ions to come off because this is a weak bond. But if we look over here, we have chromium bonded to 4 oxygens. The chromium is +6, And now, by comparison, the chromium to oxygen bonds are stronger because that chromium, being +6, is pulling electrons towards itself from the oxygens. You can talk all you want about electronegativity and that oxygen has a much greater electronegativity than chromium, but the fact of the matter is that if you take a chromium atom and you really strip it of electron density by putting oxygens around it so much, it's going to fight back, if you will. It's going to be pulling back on the electron density, and it's going to be making itself a little bit less positive than it might seem, and the oxygen to chromium bonds will be a bit stronger. And so if the oxygen chromium bonds are a bit stronger, then, and the chromium is drawing electron density towards itself a little bit more, the oxygens aren't quite as partially negative, meaning that the oxygens are going to be pulling electron density away from the hydrogen a little bit more, allowing the hydrogen to leave. Essentially, this O to H bond is a bit weaker here, and the chromium oxygen bond is stronger here compared to the weak chromium oxygen bond here and the stronger oxygen hydrogen bond here. And so as a result, our H2CrO4 is going to be acidic and our CrOH2 is going to be basic. We can make a similar argument explaining the acidity of HOCl, HClO2, HClO3, and HClO4. HOCl is less acidic than HClO2, which is less acidic than HClO3. The strongest acid is HClO4. Why? Well, if we draw a Lewis structure, we're going to have our chlorine here, and we're going to have an O, and we have an H, and the O has 2 lone pairs, and the chlorine has 3 lone pairs, and I accidentally drew an extra dot. So here, we're going to call our oxygen -2, our hydrogen is +1, and our chlorine is +1, based on oxidation numbers. Now, if we go to HClO4, we have a Cl here, we have an O and an H, we have an O, and an O. Our oxygens all have to be -2, -2, -4, -6, -8. Our hydrogen is +1, so that brings us back to +7 overall. But our chlorine is +7. Very, very, very positive in terms of its oxidation number. It's got all these oxygens pulling electron density away from it. So our chlorine to oxygen bonds are strong. Our oxygens are less negative than it might seem because of the positivity of that chlorine. And so because these oxygens are less negative, that oxygen is less negative, the hydrogen is going to lose the electron density because that oxygen is going to be really pulling on the hydrogen, and this O to H bond is very, very weak, so as to allow the H plus to fall off, and you just get to the O being negative. In this case, it's just harder to do because, yeah, you can get the H plus to leave and the O to become negative, but it's already partially negative because the Cl isn't pulling as hard. And you could, for everything in between, you could make a similar comparison. If you do out the math, we got -2 times 3 oxygens, which gives us -6. +1 hydrogen brings us down to +5, so our chlorine has to be +5. And similarly here with HClO2, our chlorine is +3 in terms of its oxidation state. So you can see in the +1 for the chlorine versus the +7, the explanation, the +3 and the +5 trend according to that. I hope this video has been helpful. Let me know if you have any questions or comments in the comment section below. Thanks for watching.